let's continue our investigation of Ohm's law and current and voltage and resistance and good stuff like that. As we said before, a battery serves as a voltage source. But unlike most other situations, I'm going to introduce a real-life complication with batteries and just discuss that briefly. And the fact of the matter is, batteries have some electrical resistance that is purely internal to the device. We're going to label this internal resistance as a lowercase letter r and examine a little bit about the impact that can have when designing an electrical circuit. This also sadly introduces a phrase that I really don't like. That phrase is called electromotive force. And I don't like that phrase because it's not a force. It's not a force, it's a voltage. Electromotive force is sometimes abbreviated EMF, and symbolically it's represented as a very script-ish letter E, capital letter E. And in a real battery, we distinguish between what the voltage the battery supplies would be if there were no internal resistance and the voltage the battery actually supplies. So this EMF, this electromotive force, is the ideal voltage of the battery. But because of this internal resistance, as the current goes through this battery, Ohm's law says that the voltage will drop by current times resistance. So we see that the voltage the battery actually supplies is equal to this EMF minus I times little r. I cannot tell you how much I hate the expression electromotive force. It is not a force. It is not a force. It is not a force. EMF is a voltage. So you have the word voltage, you have the expression electric potential, and you have the expression electromotive force. They all mean the same thing, voltage. The only difference with electromotive force is that it represents an idealized situation for the voltage coming from a battery. Okay, left a bad taste in my mouth explaining EMF, so a little something to cleanse the palate. So if we have an actual battery with an actual internal resistance and we hook it up to an actual circuit, what happens? On the lower left, we see our very first circuit diagram in this course. We have a battery with internal resistance hooked up to an external resistor represented by capital R. Symbolically, you know that a battery is represented by two parallel bars, one long and thin and the other short and thick. The resistor is represented by a zigzag. We have a resistor that is internal to the battery and is labeled lowercase r. And then we hook up an external resistance to the system, also represented as a zigzag but labeled with an uppercase r. If you have a current exiting the battery, and think of it as skiers exiting a ski lift, exiting at the thin bar, the long thin bar. If they have to go through one resistor and then another resistor, they lose a little bit of voltage going through the first resistor, they lose the remaining voltage going through the second resistor before getting to the bottom of the battery. Those two resistors effectively combine as one single resistance. It's like going downhill a little bit and then taking the actual trail downhill to the bottom of the ski lift. The total downhill is the little downhill plus the main downhill. Well, here, the resistances add together to mimic that effect. The total resistance, little r plus capital R, and according to Ohm's law, the subsequent current coming out of the battery is that idealized voltage, script E, just capital E, divided by the total resistance of little r plus capital R. If you have an internal resistance, that's going to affect the output voltage supplied by the battery. The internal resistance of the battery is going to decrease the output voltage by I times little r, but the problem is I depends upon the external resistance hooked up to the system. So there's no hard and fast formula that will tell you what the output voltage of a battery is when it's not hooked up to anything. You have to know what it's hooked up to in order to predict what the output voltage is. This tends to make internal resistance really annoying, and we won't be dealing with it in our free body diagrams. But if you ever deal with a real battery and you see that the output voltage of the battery changes when you hook it up to different circuits, it's because of this effect. There's internal resistance in the battery, and so the internal voltage drop in the battery depends upon the current, but the current depends upon the total load to which the battery is hooked up. So it's kind of complicated. This is all I want to mention about it. I just want to bring it to your attention. From here on out, we will assume that all of our batteries are ideal. They supply the voltage stated in the problem or in the circuit diagram. On the other hand, it is still possible for us to take our ideal battery and hook it up to multiple resistors. Now, if these resistors are hooked together one after the other, we would call that in series, and we can just get the total resistance of the circuit by adding up the separate resistances. So R total equals R1 plus R2 plus R3, and then we can use Ohm's law with R total to figure out the current coming out of the voltage source. Think about this. We have two identical resistors in series, and we have an electric current through the combination. How does the current in the second resistor compare to the current through the first resistor? Is the current in the second resistor equal to the current through the first resistor? Is it half the current through the first resistor? Or is it smaller than, but we don't necessarily know by how much? It's smaller than, but not necessarily half the current through the first resistor. Think about it. Think of the resistors as your trails. Think of the current as the skiers. In this scenario, in this analogy, don't worry about the skiers having accidents or anything. They can all ski perfectly well through the courses. Another way we can hook together resistors aside from series is in the example you see in the circuit diagram on the screen. It's called parallel. Notice that in the parallel combination, if a charge comes out of the top, quote-unquote, top of the battery, if the charge exits the long bar of the battery, it can circle around until it reaches a point where it has to make a decision. Does it want to follow through R1 and get to the bottom of the battery, or does it follow through R2 to get to the bottom of the battery? The charge has a choice. There are two different paths it can follow before it reaches the same concluding point. So when there's a choice, we say that the resistors are in parallel. That's different from the series. A charge that goes through the first resistor has to go through the second resistor when they're in series. But when they're in parallel, the charge has a choice. The skiing analogy is having another trail. Two separate trails served by the same ski lift. So you go up in the ski lift, and then when you exit the ski lift, you have a choice of going down one trail, maybe to your left, to get to the bottom of the ski lift and do it again. Or you can go take a right and go down the trail to your right and get to the bottom of the ski lift and go back up again. When these resistors are in parallel, the voltage drop across each resistor is the same, just as in our skiing analogy where the difference in height across the trails is the same. The trails might have different qualities. One might be more challenging than the other, but when all is said and done, if you start at the top of the ski lift and you get to the bottom of the same ski lift, no matter which trail you choose, you've descended through the same altitude. Well, in electricity, you quote-unquote descend through the same voltage difference. We can quantify this. The potential difference across R1 is the same as the potential difference across R2, and given conservation of energy is equal to the potential increase experienced by going through this ideal battery. So the potential difference across R1 has a magnitude of E, and the potential difference across R2 has a magnitude of E. And from Ohm's law, I can say that the current through R1 is equal to E over R1, and I can say that the current through R2 is equal to E divided by R2. The total current is I1 plus I2. That's the total current coming out of the battery. I1 plus I2 comes out of the battery. I1 plus I2 enters the battery. So the total current in the circuit, I1 plus I2, must be equal to the total voltage, E, divided by the total equivalent resistance, the total effective resistance of the circuit. And if we play around a little bit with the math, we can come up with a formula that allows us to calculate the effective resistance of resistors in parallel. 1 over the effective resistance is equal to 1 over R1 plus 1 over R2. We can generalize this to more than 2 resistors. If I have 5 resistors, 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 plus 1 over R5, I add all of those up, and then don't forget to take the inverse of that sum to actually get R effective. Let's think about this. We have 2 different circuits. One, we have identical bulbs that are wired together in parallel, and in the second, we have identical bulbs wired together in series. No matter how it's wired, whether it's parallel or series, it's then hooked up to a 12-volt battery. And the question is, which circuit puts out more light? Now, as a way of helping you understand this, the more current that passes through a bulb, the brighter it glows. So think about that. See if you can decide whether circuit 1 emits more light, circuit 2 emits more light, or whether they emit the same amount of light. It is, sadly, possible for you to have a mixture of resistors in series and in parallel, like in the circuit you see on the screen. In the circuit you see on the screen, there's some series, there's some parallel, and how do you go about this? There's a little bit of an art to it. You have to see the big picture, you have to break it down into the small pieces, and then you have to take those small pieces and build it back up to the big picture. Now, the big picture is a charge comes out of the battery. What happens? Imagine a charge coming out of the long, thin bar of the battery and moving up through the circuit, and the first thing it encounters is R1. All of the charges have to go through R1. They go through R1, they move around the circuit, and then they reach a point where they could go through the R2, R3 combination, or they could go through the R4 combination before reaching the bottom of the battery. Now, if they go through the R2, R3 combination, they have to go through R2, and they have to go through R3. When it's the case of have to, we have a series combination, but when it's a case of a choice, we have a parallel combination. But we have a mix, and this is where breaking it down into the individual pieces and then building it back up is key. If a charge chooses to go through the R2, R3 path, it has to go through R2, it has to go through R3. R2 and R3 are in series with just each other. But then we move towards the bigger picture and ask, okay, if the charge reaches a point where it could go through the R2, R3, or it can go through R4, that means that R4 is in parallel with the R2, R3 combination. So we have to take the resulting value from step 1 and say this equivalent resistance is in parallel with R4, and we have to figure out that combination, that parallel combination. When we can come up with an equivalent resistance for the combination of R2, R3, and R4. Well, that combination that we get at the end of step 2 is basically in series with R1, because the charge that exits the top of the battery has to go through R1, and then somehow has to make it through the R2, R3, R4 combination. So R1 must be in series with the R2, R3, R4 combination. So we would add R1 to the effective resistance of the R2, R3, R4 combination that we found at the end of step 2. Sounds complicated. It takes practice. It almost helps to anthropomorphize the charge. And think of the charge as a little character trying to travel through the circuit. And skiing, think of the resistors as trails and how it can get from the top of the ski lift, represented by the long bar of the battery, to the bottom of the ski lift, represented by the short, thick bar of the battery. So you have to go through R2 and R3 if that's the path you choose, but if I'm just going from point A to point B, I have a choice. I can go through the R2, R3, or I can go through the R4. And then finally, R1 is in series with the R2, R3, R4 combination. This looks ugly, doesn't it? We want to know the current passing through the, okay, sorry about that. I had to fix a little typo there. We can ask, what is the current passing through the 6.50 volt battery in the following circuit? And you can see the 6.50 volt battery is right next to the voltage source. Now this looks like a mess, and it is. I'll be honest, this is a mess. We imagine a charge exiting the top of the battery, and it passes through the 6.5 volt, 6.5 ohm resistor. So this 6.5 ohm resistor is in series with the rest of this circuit. But now let's imagine what happens in the rest of this circuit. Now, if ultimately I choose a path that takes me through the 2.80 ohm resistor, I then have to go through the 5 ohm resistor. So the 2.80 ohm resistor and the 5 ohm resistor must be in series, and their combined resistance, we just add them up, we get 7.80 ohms. But then this 7.80 ohm effective resistance is in parallel with this 4.50 resistor. Okay, if it's in parallel with that, I can do 1 over 4.5 plus 1 over 7.8, and I can get that the equivalent resistance is 6.38 ohms. I can continue and say that this is in parallel with a 3.030 ohm resistor. Because, again, there's a choice. I can go through the 3.30 ohm resistor, or I can go through this other mess here. 1 over 3.3, 1 over 6.38, add them up, and I get 2.18 ohms. And then in turn, this is in parallel with the 4 ohm resistor. Oh my goodness. 1 over 4 plus 1 over 2.18 equals 1.41. Now let's think about this. This was awfully messy to get to this point. But after I exit the 6.5 ohm resistor, I then want to get to the point where I could just sail into the bottom of the battery. I can do it by just going through the 4 ohm resistor. I can do it by going through the 3.30 ohm resistor. I can do it by going through the 4.50 ohm resistor. Or I can do it by going through the combined 2.8 and 5 ohm resistor. Now the fact that I the 2.8 and the 5 ohm resistor. This series combination, I've got to take care of it. It's 7.80 ohms. But now the 4 ohm, the 3.30, the 4.50, and the 7.80 ohm resistors must be in parallel with each other, because I could just go through the 4 ohm, or I can just go through the 3.30 ohm, or I can just go through the 4.50 ohm, or I can just go through the 7.80 ohm resistor and get to the bottom of the battery. So they are in parallel to each other. I can do 1 over 4 plus 1 over 3.3 plus 1 over 4.5 plus 1 over 7.8, and hopefully I get 1.41 ohms. 1 over 4 plus 1 over 3.3 plus 1 over 4.5 plus 1 over 7.8 should give you the equivalent resistance. And then that 6.50 ohm resistor, all the charges go through it. All of the charges somehow make it through that combination that has an equivalent resistance of 1.41 ohms. And so the total resistance of the circuit is the sum, 6.50 plus 1.41 equals 7.91 ohms. Now we can calculate the current coming from the battery. That's equal to the battery's voltage divided by this total resistance. So 9 over 7.91. The total current coming out of the battery is 1.14 amps. And all of that current has to go through the 6.50 ohm resistor. Let's move on and discuss energy. If you go back to the skiing analogy, there is some friction between the skis and the snow. That friction tends to be pretty low by design, but there's going to be some friction. Some gravitational potential energy is lost as the skier shushes around, making sure that their speed doesn't build up to deadly velocities. So there's going to be some loss of energy, and this energy is lost in the form of heat. And the skis actually heat up a little bit. Well, the same thing happens with charges moving through a resistor. The charges moving through a resistor keep bouncing around the different atoms and molecules in the material of the resistor, and in the process, some of their energy is lost and converted into heat. And a resistor can get hot. This is what happens in an incandescent bulb with a filament. You get the current running through the incandescent bulb, the filament itself is acting like a resistor, and it gets so hot it starts to glow. How can we determine the amount of heat, the amount of energy that is involved? Well, the heat is basically equal to the total charge passing through the resistor times the voltage across the resistor. We've seen Q delta V before. This is the amount of energy that the charges lose as they drop in voltage going through a resistor. That's where the heat comes from. As the charges move through a resistor, they lose energy, and we can calculate that by saying it's equal to the total charge times the potential drop across that resistor. But we often look at power output. And power output powers energy over time. If I could take that charge times voltage and I can divide it by time, the charge divided by time is current. And so when it comes to power, the rate at which energy is being lost is equal to the current through the resistor times the voltage difference across the resistor. This expression, power equals IV, can be re-expressed thanks to Ohm's law. We can say it's equal to I squared R, or we can say it's equal to V squared over R. Now, those latter two might look confusing. Does the power output, is it proportional to R, or is it inversely proportional to R? And as we'll see over time, keep in mind that the I represents the current through the resistance, and the V represents the potential drop across the resistor. It does not represent the potential difference supplied by the voltage source, That V in this formula represents the potential difference across the resistor. Keep that in mind. Let's take a look at this conceptual example. We have two identical bulbs hooked up to a 12-volt battery, bulbs A and B. And we turn it on and both bulbs glow. Then we hook up a wire around bulb B as you see in the picture. What happens to bulb A? Does bulb A burn more brightly? Does it remain the same level of brightness? Does it burn dimly, or does it entirely go out? Now, let's get back to discussions of power. Here we have a sufficiently annoying circuit, a 12-volt battery hooked up to 4 different resistors with a combination of series and parallel. Let's take a look. We've got to find the total resistance first. That's just a given. And if a charge chooses to go through the path with the 5.61 ohm resistor, it then has to go through the 3.93 ohm resistor. So those two are in series with each other, and they combine to create a single equivalent resistance of 9.54 ohms. The single equivalent resistance of 9.54 ohms is in parallel with the 5.38 ohm resistor. So we need to add their inverses together and then take the inverse of the sum. 1 over 5.38 plus 1 over 9.54. Add that up. Then do 1 over that sum, and you should get 3.44 ohms. So now these three resistors on the right can be replaced by a single resistor, equivalent resistance 3.44 ohms. Charges that exit the battery have to go through the 7.55 ohm resistor. They have to go through this combination that has an equivalent resistance of 3.44 ohms. The 7.55 and the equivalent 3.44 ohms are in series. The total resistance is 10.99 ohms. Now that we know the total resistance, we can figure out the current that's coming out. 12 divided by 10.99 is 1.09 amps. We have 1.09 amps coming out of the 12-volt battery, and all of those 1.09 amps pass through the 7.55 ohm resistor. But then when those 1.09 amps reach the parallel part, some of the current goes through the combination of 5.61 and 3.93, and the remainder goes through the 5.38 before they join up again. How do we determine how much current goes through each part of the parallel combination? We need to know what the potential drop across each part of the parallel combination is, because remember, in parallel, paths have the same potential difference. When you know the equivalent resistance of the parallel combination, as we do, it's 3.44 ohms, the potential difference across any path is equal to the total current entering the combination times the equivalent resistance of the combination. In our problem, all 1.09 amps enters the combination. The combination has an equivalent resistance of 3.44 ohms. So the potential drop across the combination is 3.75 volts. Now that means that the potential drop across the 5.38 resistor is 3.75 volts. And it means that the total potential drop across the 5.68 and 3.93 resistors is 3.75 volts. We lose some of the 3.75 volts as we go through the first resistor. We lose the remaining 3.75 volts as we go through the second resistor. The power emitted by the 5.38 ohm resistor, since we know the potential difference is 3.75 volts, we can take 3.75 squared divided by the resistance. We get 2.61 watts. Remember, power is measured in watts. But what about the power for each of the resistors in the series path? Well, we need to figure out the total current passing through the series path. We know the voltage drop across it is 3.75 volts, and we know the equivalent resistance of the series path is 9.54 ohms. So we can find the current through the series path. 3.75 divided by 9.54, 0.393 amps travels through that series combination. That means there's 0.393 amps passing through the 5.61 ohm resistor, and there's 0.393 amps traveling through the 3.93 ohm resistor. So we can calculate the power output for each by doing I squared times R. And the power output for the 5.61 ohm resistor is 0.866 watts, and the power output for the 3.93 ohm resistor is 0.607 watts. If you'll recall, at the bottom of the previous slide, I didn't discuss it much, but the power output through the 7.55 ohm resistor we can get from I squared R is 8.97 watts. So now we know the power output of each of the four separate resistors. But let's see if we can confirm whether or not our numbers are correct. All of the resistors, when I add up their powers, 8.97 plus 2.61 plus 0.866 plus 0.607, I get 13.1 watts. All of the resistors are dissipating power at a rate of 13.1 watts, 13.1 joules per second. The battery is supplying this energy to the system. The battery is supplying this energy to the system at a rate equal to the total current through the battery times the voltage supplied by the battery. So current times voltage, the total current through the battery is 1.09 amps. The voltage supplied by the battery is 12 volts. 1.09 times 12 is 13.1 watts. So the battery supplies 13.1 watts, and all of that 13.1 watts is dissipated in the form of heat by the resistors in the circuit. The circuit heats up, it keeps emanating energy at a rate of 13.1 joules per second, which is exactly the rate at which energy is being supplied to the circuit. Energy conservation, everything balances out. And that's it.